Even when you feel completely stationary, you are currently moving at roughly 1,000 miles per hour. That is the speed of Earth's rotation at the equator as it hurtles through space. We can see evidence of this active rotation in a Foucault pendulum. While its swing remains constant in space, the Earth turns beneath it, causing the tip to trace a different path across the floor every hour. But consider the physics of a sudden stop. What happens if the solid bedrock of the planet, the foundation of every city and mountain, instantly hits the brakes? Because of inertia, every object not anchored to the bedrock maintains its momentum. The atmosphere, the oceans, and everything on the surface would continue traveling eastward at 1,000 miles per hour, while the ground beneath them stayed still. This creates a supersonic atmospheric wave. Winds would scour the surface at speeds exceeding 1,000 miles per hour, moving faster than a nuclear explosion's shockwave. For anyone in a reinforced structure who survived the initial mechanical shock, the disaster is only beginning. The mechanical halt triggers a series of planetary-scale shifts that will soon rewrite the global map. Earth's rapid spin generates centrifugal force, distorting its shape. This outward pressure creates a permanent bulge of water and rock at the equator. If rotation stops, that pressure vanishes. Gravity becomes the only force, pulling that massive water bulge toward the poles. The oceans would immediately begin to migrate. Trillions of tons of water would retreat from the equator and surge toward the highest and lowest latitudes. This migration would unleash tsunamis reaching 100 meters in height. These waves would sweep across coastal plains, submerging entire regions as the water seeks its new equilibrium at the poles. This outward force currently maintains our sea levels. Without it, the oceans would drain from the center of the Earth and submerge the northern and southern continents under several miles of water. After several days, the oceans would settle. The water would pool into two massive polar seas, leaving the center of the planet completely dry. The global map becomes unrecognizable. Instead of separate continents, a single continuous supercontinent wraps around the equator, bordered by deep polar oceans. Because this new land sits on the remains of the equatorial bulge, its elevation would be miles above the new sea level. The air would be too thin to breathe, and without ocean currents to provide moisture, the entire landmass would become a high-altitude desert. The coastlines we recognize today are tied directly to our rotational speed. If that speed drops to zero, the water follows the pull of gravity, and the geography of the modern world disappears. Without its 24-hour rotation, Earth spends half its orbit with one side locked toward the sun. A single day lasts a year. The sun-facing side reaches 100 degrees Celsius, while the unlit dark side plummets to minus 100 degrees, encasing half the planet in ice. Our 24-hour rotation acts as a global thermostat. By constantly turning, Earth prevents any one region from absorbing too much heat or losing it all to the vacuum of space. The final threat wouldn't come from the sun or the oceans, it would come from deep within the Earth's core. Earth's independently rotating molten iron core acts as a dynamo, generating a magnetic shield that deflects lethal solar radiation. If the planet stops spinning, this dynamo grinds to a halt. The magnetic shield fades entirely, leaving the surface exposed to the vacuum of space. Without that shield, unfiltered solar wind would bombard the surface. This radiation would sterilize the land and strip away what remains of Earth's atmosphere. We rarely consider the ground moving beneath us, but this constant 1,000-mile-per-hour rotation powers the magnetic shield, preventing solar radiation from sterilizing our world.